One way to generate the solids is by rotation, called the solid of revolution. Suppose we have a region bounded by the x-axis and the curve f of x. If we take this enclosed region between A and B and rotate it about the x-axis, then we obtain a solid. To find the volume of this solid, we slice the solid perpendicular to the x-axis. The cross-section will be a circular disc, a very thin cylinder with the thickness or the height delta x, because we slice it perpendicular to the x-axis in this case. The volume of the solids is the total volumes of all of these slices. Each of the slices is a cylinder of the thickness delta x and the radius r, but r is how height the function is, and so r is f of x in this case, and the height is delta x. The volume of the cylinder is pi r squared h. The area of the disc is pi r squared, and h, the height, is delta x in this case. So v sub I is pi times r of x squared delta x. The total volume is the sum of the volume of all of these little cylinders. It is the sum as I go from 1 to n of pi r of x squared times delta x, where r of x squared times pi is the area of the circular disc. At n go to infinity, we obtain the definite integral pi from a to b r of x squared dx. R of x squared in this case is the height of the function f of x, because we slice the solids perpendicular to the x-axis and we rotate it about the x-axis, so the radius is y, or r of x. The volume is therefore pi, the integral from a to b of f of x squared dx. This is known as the disk method. If the axis of rotation is the y-axis, meaning if we take the region and rotate it about the y-axis, then we would need to slice the solid perpendicular to the y-axis. We end up with the thickness being delta y instead of delta x. The volume of the solids will be the integral from y equals c to y equals d, pi r squared dy, where r squared is the square of the radius of the slice, which needs to be expressed in terms of y, because the variable of the integration is y, dy.